this conference. We now have Sean give his last lecture.
All right. Well, indeed, it's been a long week, I guess, for many people. So this you'll be pleased to know this one probably won't take the whole hour and a half. We're nearly there. All right. So I want to spend this last lecture. I think I wanted to talk a bit about, go back to fractionalized phases. So, charge behind black holes. And as I ended last time by saying, I think that these are probably at a conceptual level, at least, the most challenging solutions that we still need to try to understand, really from a condensed matter perspective, what kind of phases of matter they represent. Okay, so these are charged black holes with or without dilitons, so including Weiss and Nordstrom, but also these more general guys. And so in particular, for this last lecture, I want to address this question from what might seem like quite a pragmatic, sort of practical point of view, but will have a conceptual undertone, which is, I just want to talk about the DC conductivity. Okay. All right, in these phases. So the DC conductivity is it's a very simple observable, right? It's the thing that appears in Ohm's law as we learnt it in school a long, long time ago. It's how does it go? The current is voltage divided by resistance, something like that. Okay, so that this guy. But this is a very right, and indeed, many of us have, been inspired by the fact that many of the most interesting materials have phase diagrams which have regions, like high temperature superconductors have regions in them where the DC resistivity as a function of temperature and in some region of the phase diagram labeled by, I don't know, whatever doping or pressure or magnetic field, whatever it happens to be, has these big regions where the resistivity is linear in temperature, okay? And this linear in temperature goes over essentially from zero temperature all the way up to when the material melts. It's observed in chemically completely distinct families of compounds. So it's a very robust, very simple behavior, but it is not the textbook behavior of what a metal should do. So a metal is supposed to have a resistivity that goes like T squared, a clean metal, where, okay, we'll say exactly when this comes out in a minute. And indeed, that's what you observe in other areas of the phase diagram. But the most interesting area of the so-called bad or strange metals are characterized by a fairly robust linear in temperature DC resistivity. So clearly, at some point, hopefully in some of our lifetimes, this really will be understood. I mean, there's like there's a simple power law in multiple different materials. There's no way it will not be amenable to understanding. So let's see if how holography might start at least to even think about this problem. We're definitely not going to answer it.
Is there anything interesting or universal about the coefficient behind that?
Possibly. So there are arguments. There are suggestions that there's some kind of bound on the coefficient. Actually,
bound is on the scattering rate, but empirically, there's an observation that the coefficient of linear resistivity scales with Tc. I don't know.
Oh well, that's something else. Okay, that's not what. Right. So yeah, there are various. That's not what I had in mind, but that's also true. So, for example, it's found that So if you take this region here and you fit the resistivity to AT plus BT squared, then which is not totally obvious why this is the kind of fit you should do to the data, but People do that. And this A, as you approach this point, goes like well, it vanishes x. Oh, so is this what you meant, Sylvia? It goes like x minus x critical. No, you meant something else.
Completely different. So
Okay,
it's
sorry.
an empirical observation by Ty Fair. Several papers. That
Yeah, that's what. I think that's what I mean.
No,
Yeah, TC. It vanishes as TC vanishes.
No. That's the value of TC at optimal doping. It
Oh,
roughly scales with the coefficient of the linear resistivity.
Oh, okay, very good. I see. Okay, that's something else. Okay.
So in different materials.
Yes, yeah, in different families even. You take the cuprates as opposed to the nictides as opposed to the organics. Somehow they all seem to scale together. TC determines how strong the linear resistivity is.
Okay, actually that's consistent. So, and it turns out that it also vanishes when TC goes to 0.
What it roughly implies that whatever is causing the mechanism of superconductivity is also causing linear resistivity.
Well, that's what Tyler would like.
Across different families of materials, which is, I guess, a good thing.
So yeah.
Resistance isn't.
Okay, so suppose you want to calculate a DC conductivity. So the immediate problem you have is the following theorem. So conservation of momentum plus, well, I'm going to be a little bit more precise about what the second criterion is, but let's say a finite charge density. Actually, what's really necessary is a finite susceptibility chi jp, so that the momentum current has some overlap. The stationary momentum current has some overlap with the electric current, but this thing is often proportional to the charge density, for example, in a relativistic theory. Right, so these things imply that the DC conductivity is infinite. Okay. And this is really an intuitive statement. Okay, there's a bunch of charge. You apply an electric field, and if there's a net charge, it just accelerates away. Okay, and you don't reach a steady state. So, but I want to give a sort of outline of a proof of this. So, firstly, there are more sophisticated treatments. So, sophisticated things you can do. Sophisticated. According to your taste, you can either use there's a hydrodynamic argument, certainly at least in the relativistic case, but I think probably in general, you can use Ward identities. Again, certainly in the relativistic case, or there's also, you can use this memory function. Memory matrix method. And those are three frameworks in which you can get the formula that I'm about to give you. But let me do it a slightly pedestrian way, which I think is rigorous, and we'll get the same results. So what's the idea? So the idea is, let's first we have to keep track of what quantities are conserved. Okay. So we have, there's going to be an energy momentum tensor that's conserved. This doesn't mean the theory is relativistic, okay? You can write the conservation law like that, and there's also a current that's conserved. Okay. So out of these currents, we can build some free conserved quantities. Right? So there's the energy. T00. There's the momentum. Oh, I'm in two space dimensions. This is the integral over space, T0I, and there's a current. The charge, Q, which is d2x J0, right? Okay, all of these guys as operators are conserved, right? E dot pi dot q dot 0. Okay. Now note that the total current Ji equals integral d2x of little ji is not conserved, right? Does not satisfy ji dot equals 0 identically as an operator equation, okay? Because it's not the time component. I'm just saying something you all know, right? The momentum it appears in two places as a conservation law, but it's also a conserved charge, right? For the I component of this equation. Okay, so ji dot, sorry, is not 0 generically. Exceptions include free theories, where basically J is the same as P. I mean, free theories, well, okay, I'll just say some free theories, and actually it's also in Fermi liquid theory. To leading order at low energies, and if you have a convex Fermi surface. Okay, I'll just put that in to keep some people happy, not because it's important to what I want to say. But for general strongly interacting theory, Ji dot as an operator is not 0. Okay, so that means the current can relax. Okay, if I apply a current, the current doesn't have to stay there. Okay, because J dot I is not 0. However, the fact that this is not true as an operator equation doesn't mean that there are not states where Ji dot might be 0 in some states. Okay, and in particular, there can be a state. There might be a state with a steady current. Okay, even though the current is not a conserved as an operator, and so specifically, there exist states with steady currents, and the obvious one in a relativistic theory would you just boost to the frame of so, I mean, I'm just sitting there with some charge and I just boost and I'm going to see a current, right? If I'm traveling towards the charge, right, I'll see a current, and that current's not going to relax. Okay, so in that state, there can be a steady, a persistent current. Okay, right, and that's in that case it is clearly tied to the momentum, right? So the picture one has is something like the following. So this is time. And so suppose you set up the system in a state with some current, some total current. So I'm going to J. So again, J with H is not 0. Okay, J, the total current is not conserved. But this state that we're going to have some formula in a second. The state that I set up with the current will also have some net momentum. Okay, because there are going to be some particles moving, right? So there's also this line is going to be J, and there's going to be a P. Okay, this state that I set up that had a current is going to have some momentum, and momentum is conserved. Okay, straight line. P with H is 0. Okay, so what's going to happen is that this current, the current is going to relax, but then it's going to stabilize because the momentum is going to keep dragging things along at some point. And so you're going to lose, right? You're going to be left with, there's going to be some final state in which the J dot is going to be steady because it's going to be tied to the conserved momentum. Okay, some particles are still going to be dragged along because the momentum can't relax. Okay, so let's just do that in simple equations. Right, so to start with, at t equals 0, we set up the state with some current J. Okay, expectation value. Okay, so to be clear here, we should it's useful to think of there's a matrix. So how would we set up a current? So there's a response matrix. So there's going to be J and P. I'm forgetting the vectors frequently. So there's a momentum and a current. And so there are going to be some Green's functions. So there'll be a JJ, a GJP, a GPJ, and a GPP. And then there's going to be some sources, which let me just write it as H of J and H of P. Okay, a source for the electric current and a source for the momentum current. So what I do when I set up this state J, right? And so what that implies at 0t is there's going to be a momentum induced. That's going to be, okay, I'll tell you what chi is in a second. Chi pj over chi jj of j. So chi pj is going to be the static susceptibility, which is the zero frequency limit of these Green's. It's just stationary. What happens for stationary state? So I just, right? Although I want t equals, okay. I set up this current. Right, let's see if I okay, this one makes sense, right? I set up the current, and the susceptibility tells me, the PJ susceptibility tells me how much momentum is generated, given the fact that I have the electric current, and I have to divide by this because, right? Because so I start off with a source for the current and no source for the momentum. Okay, I just put in the current, and so I'm going to get the J is GJJ of HJ, and P is GPJ of HJ. Okay, and then I eliminate HJ, and I get this relationship. Okay.
And the susceptibility in terms of the Green's function is the goes to.
Yeah, I'm going to get confused with this. T goes to 0, omega goes to 0. Which actually they may be the same. This one. You know, why don't I just call these chi's? Whatever I mean. Okay, there we go. It's either the omega or t goes to 0 limit. I'm just blanking right now about which one. Okay, so then I ask the same question at late times. So and then I want to know what the current is at late times. Okay, and so by late times, what I should really think of as happening at late times is that there's the momentum fixed, and it's the momentum that's going to determine. The only thing that's sort of protecting this current, the current from decaying, is the fact that it's linked to the momentum. So here I want to invert this argument, and I imagine that there's a momentum, that I have a source for the momentum. And you get a P, and you get a chi JP over chi PP. And so this was at t equals 0. So then I use that again, and actually you get chi jp squared over chi pp chi jj of j at t equals 0. And so here I've used this sort of Onsager relation that in the absence of, probably you have to assume there's no time reversal breaking, chi jp is equal to chi pj. Okay, that's just Green's function. It's a sort of symmetry of Green's functions. Okay, right. So now this, in fact, is enough to give us a delta function, because this, how the hell does this work? Right. Good. Yeah. So the green, right. So the okay. So what's the conductivity? Remember I said last time the conductivity is the current Green's function divided by omega, okay? And where the divergence comes from is if GJJP of omega goes to a constant as omega goes to 0, okay, then let's call that constant A. Then sigma will go to A over omega, and then really, there's an I here. And then we should remember that 1 over omegas always come with the delta function imaginary parts. Okay, so now I want to claim that what this line tells us is that G at omega equals 0, GJJ, so at omega equals 0 is in fact equal to chi squared JP over chi PP. So let's see if I can convince myself that that's true. Right, good. So the Green's function, the definition of the Green's function is that is that J at the current at omega is the Green's function, retarded Green's function at omega, times the source at omega. And what this tells you, the fact that there's a bit that remains constant, is telling you that J, so the omega equals 0, the omega equals 0 term is a term that doesn't depend on time, right? When you do your Fourier decomposition, you have e to the I omega t, right? And the omega equals 0 bit is the one that's time independent. And what this is telling you is that there is a constant term, right? That the Green's function, maybe one just has to think about it, but so the fact that the 0 frequency Green's function is a constant is the same as saying that there's a part of the current that's independent of time. You decompose your current into Fourier modes. There's a 0 mode. Okay, that's the mode that doesn't decay. That's the omega, the constant term. Okay, so said differently, right? J. We could decompose this current into some sum of J of modes. And this constant bit that doesn't decay is the omega equals 0 term. Okay, I'm confusing myself. Right. Good. And then this H, okay, then you have to relate this Hj back to J, and you do that with a chi. So this Hj is and so that gives you this. Okay, I feel I said the words in the wrong order, but I'm pretty sure that all the formulas I put up are in fact correct. So the upshot is the following. That this persistent current that gets dragged along by the momentum directly gives you a delta function in the conductivity that has a coefficient which is given by these susceptibilities. Okay, anyway, yes.
That coefficient of the delta weight is sometimes called the Drude weight in condensed matter. This looks a lot like what's known as the Maser bound on the Drude weight. This often comes up in the discussions of integral models. There's kind of a controversy if I have other quantities than momentum that are conserved.
Oh, good.
But here it's,
I'm assuming that there are no other conserved quantities.
Right. No, but I was just,
okay.
You're not sure if this is the same as the Maser bound or something else.
So tell me what the Maser bound is.
Well, it formally looks a lot similar. But I don't remember if it's exactly expressed in terms of the susceptibility. But it's the same idea that if you have a conserved quantity onto which the current that you're evaluating in the Kubo formula projects
Yes, then
non-zero,
yes,
then
it's the
that
same.
gives you a lower bound on the delta function in the conductivity.
Yeah, that's certainly the same idea. Absolutely. Yeah. And so actually, the reason you have to use this. I erased it. So the more rigorous way of doing it is using this memory matrix method, and the fact that it's a memory matrix rather than a memory function is precisely the fact that you need to keep track of all the conserved charges. And so, in fact, I'm about to do some umklapp scattering, and in 1+1 dimensions there are extra conserved charges, and that actually makes a difference to the resistivity in 1+1 in like Luttinger liquids, for example. So yeah. Okay, so for example, for relativistic field theory, the Ward identities, so rho Jp is just the charge density, and chi pp is E plus the energy plus the pressure. Okay, so in a relativistic field theory, you get sigma omega is rho squared E plus P delta omega, for example. Sorry, I think that wasn't very clear, but I think it should be intuitively obvious, right? That there's this momentum that doesn't decay, and that momentum just drags the current along with it, as long as there's a susceptibility that connects them. Right? Okay, but this is actually the precise formula. Okay, good. So, therefore, it follows that if you want a finite DC resistivity or conductivity, while keeping a net density, then your only option is you better break translation invariance. So what are our options here? So now, as far as we know, nature is translation invariant, right? We don't get to pick that. So any breaking of translation invariance is a question of timescales. Okay, so we cannot fundamentally break translation invariance. Right? Space-time is, as far as we know, is continuous. Well, I don't know. Maybe it is. Maybe it isn't. That should be irrelevant. So what we really need to do is break. We need to break translation invariance on the experimental time scale. So what that means is we have to be able to dump the momentum somewhere, and it better not come back until after we've done our measurement. Okay. So we need to dump the momentum. So I'm aware of at least two ways, different ways of doing that. So how can you want your charge carriers to lose their momentum, right? So one is if the charge carriers interact with parametrically heavier objects. So why does that work? So you have your charge, and then I know your big proton or something, and so the charge hits it. You can give it its momentum. The big heavy object will start moving a little bit, but much more slowly, and so the collisions, there'll be many fewer collisions in which the big object gives the momentum back to the lighter object, because it's just going less quickly, right? If it has the same momentum, bigger mass, smaller velocity, lower collision rates. Okay, that it is true. You'll see there's a factor of 1 over mass, so it's not the same to scatter this off this or this off that at fixed momentum. Okay. Right, so like this, there'll be these guys going quickly. They hit this. This starts moving a little bit, And so it's less frequent that it hits the smaller guys and gives the momentum back again. Okay, so parametrically heavier. So what are examples of parametrically heavier objects? Well, they could be impurities, or they could be a lattice of, let's say, the ions of the crystal. Okay, that's option one. Another way of dumping your momentum is to have a bath of parametrically more degrees of freedom. So there you have, for every charge carrier, you have millions of other things. So a typical collision involving the charge carrier will hit one of the other guys and will lose some momentum, but a typical collision of the other guys is with another one of their own. And so they don't, on average, give the rate at which the momentum comes back to the diluted guy. So, you know, you've got some honey and you've got some big medium and you throw something into it, it'll quickly hit something and give its momentum out, but it'll take a long time before the momentum comes back again, back to the thing that you throw in. So if you parametrically dilute your charge carriers, they can also lose their momentum over some time scale, right? Does that make sense? I'm actually not aware of other ways of doing it, but maybe there are other ways. Okay, so which one do I want to talk about? So all work, almost 99% of previous work in a holographic context has used option B quite successfully, because there are various ends floating around and you can use these large ends to your benefit, right? You can do essentially a probe approximation in which your charge carriers are much less diluted by power of n compared to everything else. So examples of two include the probe brains. So that's when your charge carriers are described by degrees of freedom living on a brain in a bulk. So I guess this was really Koch and O'Bannon. And many other works. And then the other option is, well, basically probe fermions. And this is the way the MIT crowd get a finite resistivity. So you have there the other degrees of freedom are charged, but they're not what you're looking at. So you take you have one fermion, a small number of fermions outside the black hole, this huge black hole. The fermions can fall into the black hole and lose their momentum, and they don't come back for a long time. And so the conductivity due to the fermions, which is you look at a small fraction of the whole system, right? So these are probe brains diluted by the bulk. These are probe fermions, actually, I guess, also diluted by the bulk. And there have been some interesting results. So I guess David Tong, Eva, Joe, and myself have a generalization of Koch and O'Bannon, where we got a resistivity that went like T to the 2 over Z, where Z was the IR dynamical critical exponent, and the MIT people got a resistivity that went like T to the 2 nu kf, where nu kf was the dimension of the fermion in the IR ADS2 CFT, which depended on kf. So, okay, so you can get some results. Neither of those are particularly satisfactory because, of course, you can get, there's no principle that tells you what Z is or what kf is, okay? So you can tune these models to get linear in T if you want, but there's no compelling reason why you should do that. Right, good. And also, right, and they have this dilution issue, which I don't know whether that's experimentally reasonable or not. So let's think about option 1. So okay, so option 1, possibly more experimentally relevant. Well, okay. Yeah, possibly more experimentally relevant. So
do these examples have string embeddings or
have what, sir?
string embeddings or UV descriptions?
Yes, I think so. Yeah, this is yes. You can get consistent truncations of fermions in a Rice-Nordstrom background, and this loop. Yeah, I don't see why not. And for some values of z, yes.
So what kind of data determines new KF?
Yeah, so new KF is really not a nice number because it's UV sensitive. So KF. So even though you have the right, so you have this ADS4, and then there's this ADS2 near horizon geometry. But KF is something that's determined. The profile of the wave function of the fermion that has the zero mode at the Fermi surface depends on the whole geometry. So KF is a number you get out of solving the Dirac equation in the whole Rice-Nordstrom background. And so it's right. I mean, they're typically just irrational numbers. There's a square root and things. Yeah. So this nu is some square root of 1 plus KF squared, let's say. And then KF squared you have to get by solving a differential equation. There's nothing universal. It's not, so for example, if you took out your ADS4 and had something else here, it would change. So it's not universal in the sense it doesn't only depend on the IR data. I guess Gobser would say, did say recently. So it's true that there is a string embedding where people calculated nu f and it came out as a reasonably nice number, like 1/6 or something. I forget, or square root. So this has been calculated in at least one, maybe two. I don't know, Julian.
There's the Eva, Joe, Shamet, Andreas.
That's with a lattice.
It's with a lattice.
Yeah, but that morally falls into this class, even though it's a lattice. They're not losing the momentum to the lattice. So it's, yeah, that's right. Yes.
They get new it's half.
Oh, that's right. Thank you. That's right. There is one supersymmetric construction that morally falls in this class that does get nu equals a half, actually. Yeah, sorry. That's right. Yeah, I'm sorry. But it really depends on there's some operator that has its its dimension is fixed by to be the free value.
But Kups's thing is also supersymmetric and it doesn't give you something. I don't think supersymmetric.
Let me not.
Because of exactly what you said, I think it.
No. He got a. Okay, whatever. It's some semi-nice number. I mean, nice is a subjective thing, so let's not dwell on it. But, yeah. Sorry. No.
It's also worth mentioning to get the top result. It's not enough just to get Lifshitz. You need Lifshitz in string theory rather than M theory, because we need d-branes to.
Yeah. So this
I don't know if there are Lifshitz solutions in string theory.
There will be if they're not. I mean. Anyway, so I don't want to. But this stuff out there, and it is interesting. I don't know how much it strongly connects with the experimental systems, but it's interesting. Okay.
You really want something universal, right?
Yeah. No, I like that's right. If it's not universal, reproducing the cuprates is not the only objective, right? I mean, you want to understand what strongly coupled systems do, and so on and so forth. But that's right. I mean, if you want to get a linear in T, it had better. Yeah. I mean, it had better be obvious. I mean, yeah. I think. Okay, good. So now, good. So let's go to option 1. So those are lattices and impurities, and you can do both. But many of these interesting experimental systems are purportedly very clean. So many interesting systems are apparently clean. So let's take this as an excuse to focus on the lattices. Okay. Okay, so what is a lattice and what does it do? So, right. So what in a quantum field theory, so I don't want to, of course, one way to put in a lattice is to start with a lattice model where your electrons hop between sites, but we don't want to do that. We're looking for universal physics. So within a sort of quantum field theory framework, the way you would put in a lattice is you start with your Lagrangian, with the theory that you want, and then you perturb it by a coupling that depends on space and not time, times some operator O. Okay, so you just add a position-dependent coupling for this is some operator in the theory. And now, if you're looking for universal results, you're probably going to want this operator to be irrelevant in the IR, so that the effect of the lattice can be treated as a perturbation. If it's relevant, it's just going to break up the system, and your IR is going to be a lattice system again. If you want an IR quantum field theory that remembers a little bit about the lattice, what will happen is this operator will be irrelevant. But because it's going to be the leading operator that makes something that would be infinite finite, you'd better keep it, okay, even though it's an irrelevant operator.
Can I make a comment? We added a relevant operator. But what happens is if you add a relevant operator that's spatially
in the IR, it has to be irrelevant in the IR.
No, relevant.
It was irrelevant in the UV.
Yeah, it's relevant in the UV,
but it's irrelevant in the IR. No, but that's what you'd expect.
Strangely, it's irrelevant.
Right, because you should really look in the IR.
Yeah, but usually if you add a relevant operator in the
Right,
UV, it screws up your IR. But the point is, if you had a spatially varying relevant operator, that itself is irrelevant.
No, but I think even the operator without the spatially varying becomes irrelevant in the ADS2 in the IR. So even if
the one we added just would screw up the ADS2 completely. If it wasn't spatially varying, it would just send you somewhere else.
Actually, I think the one you added might even have been unstable, right? I think it was a scalar, a neutral.
The neutral scalar above the BFL.
Not in the. Actually, I think this is a bit tangential, but the operators I'm going to talk about are going to be irrelevant in the IR. Okay. Yes, no, you're right. In your case, probably that momentum was important. Yeah. So indeed, actually close to that, it's useful to think of that, or just as a Hamiltonian in sort of frequency space. You have your Hamiltonian, which is the Hamiltonian you started with. Right, and okay, good. So we want to imagine situations where this Vx is some periodic lattice. Let's even just to make life easy, let's say it's some kind of square lattice. And so that lattice has some lattice wave vector associated to it. So let's call the lattice wave vector KL. Okay. So, it's something like e to the I KLX, possibly with some pi's or something. And so what you're going to get when you Fourier transform this, so if I write in momentum space, this operator is only being inserted at momentum, at the lattice momentum, okay? Because I'm imagining that this guy, that V of x is oscillating with a single frequency, that's called a lattice. Right, so when I write this coupling in momentum, okay, I'm just writing in momentum space here is really all I'm doing. You're adding the operator at a particular momentum. Okay, you're not adding a homogeneous operator, you're adding an operator with momentum to the theory. Okay, which clearly is going to break translation invariance. So you see, lattices is somewhat special. The difference, say, between lattices and impurities is that even though they break momentum conservation, they do so in quite a specific way, right? There's a single lattice wave vector in the problem. So the lattice breaks translation variance but it can only absorb momentum in units of KL. That's a multiple of KL. So for example, in the case of free electrons, this manifests itself that you have the lattice momentum, okay, that is conserved, but the physical momentum isn't. The lattice momentum is defined sort of mod KL, okay, so processes, so umklapp processes are processes where your theory scatters off the lattice in such a way that it loses momentum KL. Like it basically bounces back off the lattice. Okay, so now, well, this shows up in a technical way, which I'm not going to go through, but I hope that it's plausible. So you can show that gamma, which is going to be the rate at which you lose momentum, is given by, oh, I should have put it, let me just stick a G there. The rate at which you lose momentum through these umklapp processes is given by G squared KL squared times the limit as omega goes to 0, the imaginary part of the retarded Green function of the operator that couples to the lattice at that frequency and at the lattice wave vector divided by omega. Okay, so if you want, you can look in my paper with Diego Hoffman, for instance, for a derivation of this. But the idea is it should be very plausible. So what is this saying? That the rate at which, okay, so the imaginary part of the retarded Green function is the spectral density, okay? That tells you how many degrees of freedom there are in the system that have an overlap with this operator and at a given energy and a given momentum. Okay, this is the spectral density. Okay, now the things that dominate are going to be, because we're really interested in the DC conductivity, so the thing that resolves this delta function at 0 frequency depend on the low energy degrees of freedom. Okay, so that means we want the low energy degrees of freedom in the system. And what the lattice sees, so if you send your charge carriers through the lattice, the only degrees of freedom that see the lattice are, in terms of losing momentum, are the ones that are at the lattice momentum. Okay, so the rate at which, right? Okay, so the rate at which your system loses momentum depends on the number of low energy degrees of freedom living at the lattice momentum. Okay, and that's related to this fact that the loss of momentum happens through these umklapp processes in which you scatter things by KL. Okay.
You're interested in optical conductivity. That formula still holds.
So okay, let me define this gamma, and then let's. So yeah, if omega is small enough, you can probably use this formula. So let me show you what that'll be. Okay, so, and then once you've got this gamma, the DC conductivity is what we had before, is these susceptibilities. But now, instead of the 1 over omega, you get this rate of relaxing momentum. So this delta, so we had some conductivity with some, let's say, even the conductivity that we calculated yesterday that had this delta function here, that delta function will now get resolved into some kind of Drude peak, and the height of this Drude peak is this formula, and it depends on 1 over gamma, where gamma was this momentum relaxation rate. Okay, so this is why it's tricky. So okay, this formula, right, as you might have guessed, is perturbative in this coupling G. Okay, so this formula will be valid if this operator O is irrelevant at low energies, right? So this formula, if O at KL, as David was stressing, is irrelevant. Then at these low energies, you can treat it perturbatively.
So that means that somehow you don't have like a tight binding limit.
I don't. That's right. This is definitely not. This is a long way. Exactly. This is a near hydrodynamic limit. It's like all the interactions happen. The currents relax, except the momentum, and then the momentum's relax at the end. Yeah. Exactly. Right. So that's what we see, that when gamma goes, as you turn off the lattice, gamma goes to 0. Right, and the conductivity diverges. So. Right. Okay, so it's an irrelevant operator, but it controls the divergence. And the main thing is when you want to do this calculation is that obviously you can't calculate the conductivity perturbatively in a quantity because it goes like 1 over that quantity. So this whole memory function business, one important thing is you just write the conductivity as 1 over omega m, and then it's this guy, the sort of self-energy like quantity that has a good expansion as g goes to 0. Okay, so this thing ends up going like g squared, and then when you set omega to 0, you get that.
Can you estimate the width of the peak as well using some
I think so. So this memory function, so what this really is, if I took out this omega, this would be the memory function, which is this thing that's here. And there's probably some range. Okay, honestly, I don't know how far out you get, and in particular, I'm not. Well, as we discussed, I'm not sure whether you really see this thing going down. So I'm not sure you get.
Well, I mean, if there's only one long mode, then it's just a Lorentzian.
Yeah, but I guess what he secretly asked. Okay, he might or might not have been secretly asking is this. So David and Gary Horowitz and someone else did this very interesting paper very recently, 2 weeks ago, where, as well as confirming that we got the right answers for the DC conductivity, they also found that this optical conductivity had a pretty non-trivial slope, had a 1 over omega to the 2/3. And there's a question, this doesn't seem to be captured by this kind of formula. That's right. So you can't go too, I just meant you can't go too, I think you can get some window of frequencies here, but not too many.
I should say we start by getting a perfect Drude peak up to a width of 2 times your.
Yeah, I guess that the Drude
and
peak.
it turns over to this.
Right. So I think the Drude peak. This thing. This thing should be reliable. Yeah. Okay. So, right. So now we've got a formula. Okay. So this is basically the resistivity, right? So the resistivity is one of the conductivity, which goes like this quantity gamma. So now let's see, right, what do we want to get? So T squared is actually a pretty large, it's a power law resistivity, it's pretty large at low temperatures, and these strange metals that go like T are even more resistive. So what we're really trying to do to get a power law resistivity, what we see is that there have to be a lot of low energy degrees of freedom at finite momentum. Okay, if you want to, so let's see how this works for the Fermi surface. Okay, so let's, as a sanity check of this formula, which I should say there's a slight caveat when you apply it to Fermi liquids due to this fact that the current is actually conserved for convex Fermi surface. But I think that only changes numerical prefactors. So what I'm about to do is not 100% legitimate, but I think it is okay. And it gives the right answer, so. All right. So the moral is, a large, which means, by which I mean, let's say power law in T as opposed to exponentially small, resistivity needs low energy degrees of freedom at k lattice. Okay. Right. So let's do Fermi liquid theory. Okay. And let's see if we can get the T squared out of this formula. So what are the operators so Fermi liquid theory is just free fermions with a Fermi surface. So the first operator, so the action, okay, so to be specific, the action is something like in momentum space, so there's going to be two momenta and an energy, some dispersion relation, E of P, psi dagger P, psi dagger psi, right? With P's and minus P's in the right places. Okay, so that's a free fermion. Right, so, okay, sorry, of course, well, yeah, okay, let's just write it like that. What was I about to say? Okay, good. So what operators do you have in this theory? So the first operator you might think of, so what could O be? I need some operator to couple to the lattice. So, and the more relevant, the bigger effect it will have. So the first one you could write down would just be the charge density at finite k. And so the charge density is d3p psi dagger p plus k psi of p. Again, after some minus signs and so on. Okay, so what about this operator? So this operator turns out to be relevant in Fermi liquid theory, okay? And let's see if we can even get that out. So the thing about Fermi liquid theory, there's a Fermi surface, and you're supposed to scale your momenta to the Fermi surface, and the momenta parallel along the Fermi surface don't scale, okay? So that changes the counting a little bit. So of these three P's, you scale energy, and so there's a P perp and a P parallel. And let's not scale P parallel. So this goes like 2, 3. So the dimension of psi is 3/2. Okay. And so here, well, it's just obvious that this guy is relevant because it goes like energy. I mean, this is the same. This is just a kinetic. This is like adding the kinetic term without the omega in front. I mean, sorry, this is just a kinetic term. Right? Okay. It's definitely. Let me. Okay, this operator is relevant.
That's how you scale things for a Fermi liquid. You have to
Sorry?
scale linearly with momenta. It's like a 1D system. It's not like a 3D system ever.
Sorry, sir?
You don't scale momenta of Fermi surfaces that way.
I think so.
Scale
So
it feels like a one-dimensional system.
yeah, that's what I just did. Yeah, so that's why. That's right. So of these three, I scaled the energy and P perp, but not P parallel. So it is one. That's what I did. Yeah. Okay, so this operator is relevant. So what? Right. Okay, and so that's the first point. And secondly, what does this operator do? So the Fermi surface has so there's KL. Okay, there's a lattice guy. Then there's another K, which is KF. Okay, and the nice thing about the Fermi surface, all the light degrees of freedom are living on the Fermi surface. And you could imagine that 2 points on the Fermi surface might be connected by KL, okay? And that means that that's what this current, this charge density operator takes a guy there and moves it there. Okay, that's what this psi dagger psi does. So this will couple strongly to the lattice, and there will be low energy degrees of freedom that this operator connects with KL, as long as KL is less than KF, I guess. However, because it's relevant, okay, that means that we should have already taken this into account. And in fact, what this will do is it will have a drastic effect, and it'll actually gap the Fermi surface at the points it connects. And I don't know if this picture is quite right, but you sort of have to redraw the Fermi surface, having already taken into account. Said differently, if you've got some fermions in the lattice, you'd better calculate your Fermi surface with taking into account the lattice. Okay, the lattice can bend, can fold, changes the Fermi surface. So if we've done our calculation correctly in the Fermi liquid theory, there will not be any points on the Fermi surface that are connected by lattice vectors in this way, because they will have been gapped out by this relevant operator. Okay, so this operator should have already been included in when we constructed the Fermi surface. Okay. So then you go to the next one, and so the next operator is psi to the fourth. Okay, so this one was relevant. Okay, so again, this relevant operators, if there are low energy degrees of freedom that they can connect to, have strong, just totally change the IR. So we have to then take this modified IR and then do the calculation about that point. Okay, so lattices, bend, change the Fermi surface. So suppose we've already done that, then the next operator is psi dagger, psi dagger, psi psi. Oh, sorry. That's with some momentum p is right. So we have to write it like follows. They're going to be 4 guys, which each have their 3 momentum. And there's going to be psi dagger P1, psi dagger P2, psi P3, psi P4, such that the total momentum is equal to this external guy P. Okay, that's the quartic operator of Fermi liquid theory with some momentum. All right, so what's the dimension of this operator? So, okay, one has to be a little careful because scaling in Fermi liquid theory is not the same as usual. So we scale towards the Fermi surface. So you get 2 from each of these. So that's 8. Oh, sorry, okay. This whole thing has to be, so there's 8. These guys all, oh, sorry, that should have been minus 3/2 up there, obviously, right? The action should have 0 scaling. So that 3/2 came from the 2 plus 1. So there's minus 4 times 3/2, which are these guys. And then of these delta functions, only, that's minus, yeah, okay. Now, the delta functions, it turns out that the energy one, that certainly scales, and that gives you a -1. But the momenta, neither of the momenta scale, because they're not scaling towards the Fermi, because we've got this P here. So when these PIs scale to the Fermi surface, there's this P left over, and you just get delta of P, not delta of something you're integrating over, and that doesn't contribute. So it turns out that the dimension of this guy is actually 1, okay? You can do this slowly at your leisure, but that's correct. This quartic operator is irrelevant. This is why Fermi liquid theory is stable, okay? The first interaction that you add is an irrelevant operator, right? That's why you get omega squared for the imaginary part. Okay, so this was the momentum space operator. So now you have to Fourier transform, let's just Fourier transform the energy. Okay, so I'm only doing this to keep track of dimensions. So the Fourier transform for the energy is like d e to the I omega t of the operator of p. So there's an omega here, so that increases the dimension by 1, right? So the dimension of the operator in position space is now 2. Okay? Now we're ready to get the Green's function, because I want to do a scaling argument on this. Okay, that's where we're heading. So now the Green's function of this operator is, again, just keeping track, is dt of O e to the minus I omega t. And so it's O, so that's 4 minus 1, right? So the dimension of the Green's function is in fact 3. Okay. Now, in this formula, we're told to take the imaginary part of the Green's function, the low frequency limit. The imaginary part of the Green's function is always odd in frequency. So there's going to be 1 power of omega that will cancel this omega here. So you can see we're just about to get this t squared, right? Because, so if we think of this guy where it scales well, right? So it scales well below the chemical potential. So the two things, right? So that implies that this Green's function thought of as low, it's going to go like, right, it has dimension 3, and it has to be odd. So the simplest thing is it goes like omega times t squared to make up the dimensions. Okay, and so now if you plug that into that formula, you get that the scattering rate goes like t squared, which is the Fermi liquid, which is this famous Fermi liquid result. Okay, but this is really not trivial. Okay, so I mean, so what's easy is to find out that the lifetime of the particle in Fermi liquid theory, you get this I omega squared. Okay, that the imaginary part of the interactions, the width, that's the pole, right, that we talked about before. It goes like omega squared. This omega squared has nothing, you haven't broken translation variance in this formula. So this formula is not enough to get you the DC conductivity. Okay, you cannot just say this omega becomes a T, and that's the lifetime. Okay, you need to put in the lattice, all right? And the only way that the lattice was able to efficiently degrade in Fermi liquid theory is that there's a process where you can take 2 fermions. So this quartic operator takes 2 fermions and moves them somewhere else, right? And that keeps, you can do that as long as K lattice is less than 2 kF. Let's just say for a spherical Fermi surface, you could take 2 fermions, shift them by a total momentum KL, and stay on the Fermi surface, so you still have your spectral weight. Okay, so the reason that this quartic operator can have spectral weight is because the degrees of freedom are extended in momentum space. Okay, so this T squared requires an interplay between 2 momenta. Okay, between KF and KL. All right, and if they don't both go into the problem, you're not going to get this T squared. All right.
What about anomalous dimensions?
Anomalous dimensions. Isn't it a free theory? I mean, it's okay.
Oh, because you showed that the leading interaction.
Indeed,
I
but
see.
indeed, you could imagine generalizing this to non-Fermi liquids, and then you could definitely. I think this would be the right way to calculate the DC conductivity in a non-Fermi liquid, is to plug it through this formula, and indeed use the corrected dimensions, which actually I haven't seen.
So the point is that the only interaction that could give you an anomalous dimension has been incorporated into this reshaping of the Fermi surface. Because otherwise you'd
Oh, this
expect
JT, well, that's just relevant, yeah, and then everything else is irrelevant. Well, more or less modular BCS things, but yeah. No, this is correct, I think, right? But anyway, I just want to say that this T squared is, that there's really some physics that goes into it. It involves an interplay between 2 different momenta. Okay.
Said another way, if you had a lattice much bigger than
Yeah, exactly. Yeah, then it wouldn't work. That's right.
KL
No, that's right. No, that's what. K, right. Depends what you mean by big lattice.
you would
yeah. That's right.
you wouldn't get T squared.
That's right. That's right. Yeah,
Could
exactly.
you explain again why the Green's function has to be odd?
Oh no. I'm sorry. It's the imaginary part of the Green's function. I think the proof is like three lines, but I'll show you a reference later.
As long as the operator O is bosonic.
Sure, yeah, with some assumptions about for bosonic operators. Yeah. Yes.
Do multiples of KL show up in deforming the Fermi liquid?
Deforming? What do you mean deforming?
So like KL is much, if it's a lot less than 2 KF, there's 2 KL and 3 KL.
Oh, there could be higher. There could be higher operators. You mean, like psi to the 8 or something? No. What? I'm sorry, I didn't understand that question.
So this the potential was a lattice, right? In
Yes.
this operatorship. You said multiples of KL up there.
Right. So this one has the KL is the sort of the unit. I mean, the simplest thing. You could have like multiple scatterings. So the ones with multiple KLs are just described by this process happening multiple times, but it won't change the power. Yes.
Probably a stupid question, but why can't this imaginary part of Green's function be omega cubed? It'll also
No,
be
that's
odd.
right. So I mean, you can do the calculation in Fermi liquid theory, but this is there should be some reason for it to vanish, I guess. Good. Okay, so what about holography? okay, so before I get to holography, because it's not related to holography. So let's say you had the everything in your theory was bosonic, and that so fermions had this dispersion relation, this sort of k minus kf. But suppose that everything went like omega went like k to the z. Okay, so you had some bosonic degrees of freedom. Then, right, so there's nothing, if we stick k equals to kl, omega, this is a big scale, this is like a UV scale, okay, it's a lattice scale. So this requires, it costs you a large amount of energy to take a boson, even a critical boson, and give it a lattice momentum, because the lattice momentum is a lot of momentum, okay, so there's a kinetic energy cost to having momentum. So what that means is that the degrees of freedom, so they will show up in this OO two-point function of 0 and KL. What you'd expect is that the only way, right, at low energy, if you're at 0 temperature, there'd just be nothing there. At finite temperature, there's always some probability of finding these excited states, but it will be Boltzmann suppressed. So what you'd expect is that the spectral density will go like E to the minus KL to the Z over the temperature, okay? Because that's the Boltzmann factor associated with producing one of these guys, right? So if I have a boson and stick it at some large momentum, it's just very off shell, okay? So it's hard to produce it, and you get an exponentially small spectral weight. So if I take some critical bosons and throw them and try to drive them through a lattice, I'm going to get a resistivity that's exponentially small, because the bosons basically just don't see the lattice. Okay, they don't scatter efficiently off the lattice. Yes?
Even these bosons are sharp. I mean, you can't say this in general.
I'm just saying that all the critical degrees of freedom have this dispersion relation.
Yeah, well, but there could be a power law decay in the spectral weight about that peak, your omega scales as kz.
Omega. Sorry, say again?
It can be any function of k to the z over t. It doesn't have to be exponential. The answer you say is e to the minus k to the power z over t. That's not true. It can be any function. Not just exponential for certain models, but make certain assumptions.
So what's wrong with the argument that it has to be that it's a
Well,
Boltzmann?
you're assuming that there's a sharp boson excitation at energy k to the z.
Oh yeah, sure.
That's
Yes, I understand what you're saying.
System, that's not true.
Yes, I understand. Yes, very good. So let's say you have a free boson that's a delta function on this light cone. Absolutely. Yeah, good, of course, good. So what we're saying, right, is that if the 0 temperature theory, well, I'll draw a light cone. Let's pretend the z is 1 per second, has some omega k cone. So if it's localized here, then you're fine, but if it's strongly interacting, then right, there could be some smeared spectral weight that. Okay, but yes. Okay, so now let's go to holography, so where we can calculate these things. So for example, a case where this was calculated and you get this is in this 1D Lattinger liquid, when it's at half filling and the bosons are exactly living at the lattice KL, then you get a power law. But when it's away from half filling in the Lattinger liquid, you do get this exponential suppression. And that's not a, okay, I know there's at least one example where you get this kind of behavior. Okay, so holography, right? So remember, our original objective now is that we want to try to understand these various exotic black holes that have many interesting properties that I and Subir and John have been talking about. And so these, as has been understood, pretty recently in the last year or two, the near horizon metric of these black holes typically has a scaling form, which can be Lifshitz in general with some z. And then in general, there can be a sort of overall anomalous scaling in the metric. So that the metric is scale covariant but not invariant. And this guy is related to this theta, this hyperscaling exponent that I imagine Subir talked about. Okay. So now these geometries, right, the scaling invariance of these geometries is that x goes to lambda x and t goes to lambda to the z. Sorry. Oh, did I get, no. I always get these z's in the wrong place. Is that, no, that's okay, good. So it looks like that it is the case that as you go to low energy in all of these models, you're scaling towards the origin in momentum space. So when omega goes to 0, k is also going to 0. Okay, unless z is infinity, in which case x does not scale and t does scale. So I think I thought of so z equals infinity is like it's an overambitious Fermi surface. Okay, so see, a boson has degrees of freedom at a point. A Fermi surface has degrees of freedom, low energy degrees of freedom at the surface in momentum space. And z equals infinity just has degrees of freedom everywhere. Okay, so all k are critical when z is infinity. It's a locally critical theory. Okay, so it's like it has even more low energy degrees of freedom than a Fermi surface. Okay.
Does it make sense?
Sorry?
Does it make sense?
Well, okay. Let me show you what kind of space-time. So everybody's until 4 years ago, every string theorist's favorite space-time was extremal black holes, right? And these extremal black holes all have radius 2 in them, which has z equals infinity. So so it shows up. But let me that's not necessary. So what? Okay, I'm going to come back to the general case in a second. So in particular, z equals infinity includes Weisser-Nordström, which has this is ADS2 cross R2 near horizon geometry, which has infamously, so S, the entropy density goes like T to the, I'm going to be in 2 dimensions, 2 minus theta over Z. So Weisser-Nordström has z equals infinity, has theta equals 0. So the entropy, so this goes like T to the 0, and that's why there's
Theta equals D. But anyway.
No, I think it's 0.
No, because it doesn't, because there's a volume law for the entanglement entropy. I just worked this through.
No, I know it has a volume law for entanglement, but it's a pretty special case for the entanglement entropy. I mean, there's no question. I mean, let me put it this way: the metric doesn't scale, right? So theta is 0. Okay, let me put it this way. So
a different coordinate.
The metric goes like lambda to some number that's proportional to theta. Sorry?
No, I mean the
theta is definitely 0.
Choice of r, you can make a different choice of r, right? Is it the same coordinate?
Go on. Probably this is irrelevant.
Okay. I think theta is 0 for these backgrounds. And so what happens is you get right, C equals 0. Good. So another option with z equals infinity. So this would happen for any finite theta. So another thing you can do is take theta to minus infinity as you take z to infinity, keeping theta minus theta over z, let's call that eta fixed. And so what this corresponds to are spacetimes that are conformal to ADS2 plus R2. So you have R to some power times ADS2 plus R2. And these guys, the entropy density goes like T to the eta to 0 at low temperatures, so it goes to 0. Okay? So z equals infinity is not synonymous necessarily with the ground state entropy density. Okay? Good. And right, both of these, in fact, this one, as I just learned earlier today, this can also be realized in string theory, this background. Okay, so right. So just finally, let's compute some Green's functions. So what we'd like to calculate has not quite been calculated yet, but hopefully it will soon. So in this formula, the natural operator to couple to the lattice is just the charge density, Jt, which is irrelevant in the IR theory in these models. Right, so you'd like to calculate this imaginary part, gr jt at finite temperature. That's a little is doable, but it's a bit tricky. So what we're going to do first, that should have the same information, is calculate the t equals 0 Green's functions, but as a function of frequency and k. Okay, to look at precisely this thing. So we were saying that would tell us at 0 temperature how smeared the light cones are and whether there are degrees of freedom away from the strict on-shell light cone. Good. So using essentially the same methods that I showed in the first lecture, how you calculate these retarded Green's functions, it turned out that a simpler thing to calculate than the density is the Green's function of the x components of jx, okay, as a function of omega and k at t equals 0. Okay, as a kind of warm-up to okay, sorry, I should say, we did calculate, sorry. So for Weitzer-Nordstrom, the ADS2 case, you can calculate that. Sorry, yeah, I should have said that. And you get t to 2 times the dimension of the dimension of Jt in the ADS2 theory evaluated at the lattice momentum. Okay. So this formula looks deceptively similar to this MIT formula, which also is t to the 2 times an IR dimension that depended on k, but it's physically a totally different object. Okay, this is not a kf that appears here because there's no kf, it's a kl. Okay, so if you take these, so these locally critical theories have tons of degrees of freedom at finite momentum and low energy, like more than Fermi liquid theory. And by a very similar dimensional analysis argument, or you can just do the calculation, you find that, right, so the DC resistivity of a theory that has an ADS2 cross R2 near horizon geometry is given by, it's a power law in the temperature, but the power law is not a universal quantity, it depends on the lattice, okay? Right. And this formula was confirmed numerically by David Tong, Gary Horowitz, and George Santos, it seems. So you can get a large, so as you might have expected, a z equals infinity theory does give you a power law resistivity, but the power is not universal, so it's not as nice. You see, this Fermi surface is really nice because you can connect all these different points, and that kind of washes out the KL. And when you're left with z equals infinity, sort of all the K's are separate, and you just pick up the KL. So, if you want, I really don't know any other way of getting a robust power law. By robust, I mean, generally IR that doesn't involve a Fermi surface explicitly in the calculation. Okay, so I'm pretty sure that this result, although we haven't done it yet, also holds for these cases that are conformal to ADS2 cross R2. Okay, I'm pretty sure, but it doesn't exist yet. But then let's do all the other cases. So when Right, so let's calculate this guy, and let's calculate the limit as omega goes to 0 with k fixed. Okay, and so that's exactly looking at, so there's this dispersion relation, omega goes like k to the z, and now what happens if we sort of go a long way off the light cone? Okay, and set omega to 0, so we're down, I guess we're down here. Omega to, which one's omega? This one. No, this one. Right. So we're going to be a low omega, but at finite k. So we go down here, and let's see how smeared the light cone is. So it turns out you can actually, it's not totally straightforward, but you can do the calculation holographically. And okay, so there's theta and z are the two parameters. And so what you get, which actually for some technical reason, we needed something like theta plus z equals 4.
What model are you using?
These ones, the dilaton, your ones. The dilaton coupled, dilaton Einstein Maxwell dilaton. So, right, okay. So it turns out that in the limit omega goes to 0, k fixed actually is actually in fact always a WKB limit of the form of the Schrodinger equation that you get. That's not an approximation. It's just that is what this limit corresponds to. And right, so what you find is that there's a probability for right. So this imaginary part is basically how quickly it falls into the black hole. Okay, and so roughly what happens is that there's this sort of this Lifshitz throat that's collapsing with this sort of characteristic dispersion relation, and you're sending in a wave that sort of has too much momentum, and it just isn't able to fall into the black hole very efficiently. And so what you get is that this thing goes like e to the minus kl over omega to the z and to the 1 over z. So for example, this is as Subir was saying. So it's not, you don't always get a 1 over, like naively you might have said it should be 1 over omega here. Okay, it's 1 over omega to the 1 over z. Okay, so you get that.
WKB calculation?
Sorry, sir?
Is it the WKB calculation?
Right, so what appears in the Schrodinger equation as this guy, kl to the z over omega, sits in the equation as a WKB parameter, and so you can do that. And so right, so the point is that the spectral weight off the on-shell condition is exponentially small. And actually, this formula has been seen before. And for example, so Faulkner and Bolchinski, I think, were probably the first. They were looking at fermions. So here you have to calculate some two-point function of the gauge fields, right? That's what goes. Okay. What goes into that? So basically, just 2 seconds. Waves that carry a finite momentum don't easily fit into a Lifshitz singularity, and it's because the horizon has 0 size. Okay, it's not like an ADS 2 black hole where the horizon has a finite size where the modes can just fall in. Here the horizon is 0 size. Actually, that should go backwards, right? Okay. Anyway, modes with large momentum at low energy don't like to fall into Lifshitz horizons. Yeah.
Yeah, so is this exponential behavior somehow an artifact of the fact that you don't have asymptotically ADS geometry? Like
it's independent of the asymptotic geometry.
I mean, so you're saying that if you consider a metric where this is in the IR and if you have ADS, you'd still see the exponential.
Yes. Because the imaginary part of the Green's, so intuitively it's because the imaginary part of the Green's function is due to things that fall into the black hole. It's the dissipation, and that's determined by the IR geometry at low energies. Okay, and more generally, there's a matching procedure. So in general, it's true that the full Green's function is equal to some expansion in omega plus the IR Green's function divided by.
Exactly. Yes.
You always get something like this. okay? And these guys are all real. And so the imaginary part of this ends up being just being proportional to the imaginary part of the IR guy. So it's really independent of what happens at infinity. So all these guys are all real because they come from solving the equation away from the horizon, and then there's no dissipation. All the imaginary parts come in from these ingoing and outgoing boundary conditions at the horizon. That's the only place where eyes come into these equations. And so when you solve it in the far region, away from the horizon, it's just everything's just real. I can give you some references. I mean, this is just true. Okay, so I'm despite what I said, I'm running over. So good. So okay, so there's some. I think the following statement is true, that we don't have a holographic model of a fractionalized of where the charge is behind the horizon, where the frequency space Green's function, the momentum space Green's function, a leading order large n, so classically, looks anything like there's a Fermi surface. Okay. In the sense that there's no spectral weight at zero temperature and finite momentum and low energies. I was trying to be very careful. That doesn't mean that it might not be there, that these are very interesting. The entanglement entropy is very interesting that Subir talks about, and somehow I think there's an immediate challenge in the future, which is trying to pierce together these systems that have some features that look like they're Fermi surfaces and other features that don't. And well, we have to make sense of that. So I think there really are challenges, which, I mean, if we want to connect with the phenomenology, having degrees of freedom with finite momentum, low energy degrees of freedom with finite momentum, is both a conceptually central point of a Fermi surface, but it's also a phenomenologically central point of a Fermi surface, because that's where these robust power laws in T come from. So it would be really nice to have something, where there was really an honest KF, something that looked like it was a Fermi surface in holography. Okay, and so we have these kind of, as I said, overambitious Fermi surfaces where there's lots of stuff, too much stuff. So we need to find this balance, right? That there's some stuff at finite momentum, but maybe not too much. Okay, that's all. Yeah. And just to preempt questions as the last speaker, I think I have to thank Julian and David, who have put in a lot of work to make this happen, so we should definitely thank them.
Any questions? Yes.
Seth, how do you understand the conformal ADS case and the special relation is the flat, no? But
sorry, I can't hear what you're saying.
The conformal ADS case,
yes.
Special relation is still flat.
So the what's flat?
The special relation, omega is k to the z.
Yes. So the scaling, yes. So the metric scale. So x goes to lambda, goes to x. T goes to lambda t, R goes to lambda t, and the s squared goes to lambda to some power. Depends on this eta, but I don't remember offhand. So you think of it, right? Okay, that's how you think of it. You might, I think what you're worried probably, and it's true that it looks like you should really scale x as well, because there's some r's in front of the dx's, right? But this is the fact, the way that you can be sure that this is the right way to look at it is that when you calculate the spectral functions, that they look like the ADS2 ones. That they have this k appears as a weight, not as a.
Shouldn't you be worried that if you have some scaling with the metric scales, that this will be broken in a higher derivative order and hence by finite quantity effect?
That's yes. Okay, two things. I think this. Right. So there's like this. There's a loop. there's a sort of vicious circle wherein up to a comment that I'll come back to in a second. Until recently, ADS2 is only regular charged horizon geometry. Okay, so where could these things land? So suppose some stringy, some physics resolves a singularity. Where's it going to take you? In all known cases, probably to ADS2. But we know that ADS2 cannot be stable at the lowest energies. Actually, I haven't said that, but you can prove that when you have this equals infinity scaling with a finite ground state entropy, that the density of states diverges at the lowest energy scales, and there generically has to be an instability. So where can that take you? But, back here. So there's been, I think, really a confusion about what the true IR of these things should be. And maybe, of course, the less pleasant options is that the system might be gapped. It might just close off generically, or it might break isotropy. You might go to inhomogeneous phase generically. Those would be fun things. Right, so there's some confusion there if you try to get all the way to the IR. Now, as I think came up in Subir's talk, it's been pointed out that there's one case which is in 2 dimensions. So when theta equals 1, that's Subir's special value, or I should say Subir and Tadashi Nagida's special value, where you get the log entire entropy. And if you have z equals 3/2, okay, the geometry seems to be regular in the IR. And it's a pretty weird, I don't know, someone who knows GR, okay, and well, there's an interesting space-time which actually I don't really understand what it's doing. It's not AES2. There's some other space-time that seems to be regular, and that may be a way out that definitely makes some people happy. And maybe, so there might be another endpoint that's regular and not AES2. That would be nice. That's another possibility. But they're like no paper, but it hasn't been studied.
Any further questions? Any last words? Okay.
I have some last words, actually. I just want to say 2 things before you all leave. Firstly, when Julian and I were designing or sort of deciding, organising this workshop, we were kind of selfish. We just invited the people we wanted to hear to talk about the things we wanted to learn. So sort of by design, Julian and I have had a great time, and I just really hope that you've had as good a time as we have. The second thing I want to say is that Sean actually made a mistake at the end of your lecture. It wasn't hard work for us at all. We sent literally 6 emails, and that was it. So all the hard work was done by the people on the front desk, in particular Al-Marie, Jenny, Christine, I'm missing people, and Chia, of course, and Steve, who sat in the back and has watched every single lecture over the last week. He must be one of the few here. I'd just like to say a big thank you to all of the speakers, and in particular to the people out the front.